Hello and welcome to this revision session for AQA A-Level Physics on the topic of waves in Paper 1, in particular looking at refraction, diffraction and interference. So if we've been successful and we've learned in today's lesson, we should be able to answer A-Level Physics examination style questions, assess our understanding on A-Level Physics and understand what topics we need to improve upon for A-Level Physics. So how should you prepare for this revision session? When you're completing your work in this revision session, divide your piece of paper into two sections. Make the section on the left hand side larger than the right hand side. And in this left hand side section, write down your work and out and answers to the questions in the revision session. When you're doing this, make sure you write your answers in full sentences and show full working out. Whilst in the right hand side, write down any bits of information or any hints and tips on answering questions from this revision session, and after the end of the revision session write up these notes into a revision sheet for you to use independently. So how should you be revising for AQA A-Level Physics? Well, the first step is to look at the knowledge, learn the key facts, use your Vision Guides class workbook, student prep notes and a textbook to learn the key ideas of the course. You may wish to make mind maps or write out notes yourself. The second step is to test yourself. Use things like Caboodle, Seneca, the Student Knowledge Checker to quickly test your own knowledge, and you may wish to do this from your own cue cards. Then finally, practice exam style questions. Use exam prep books, homework books, supervised study books, additional workbooks to answer questions and mark your own work, and you may wish to download your own exam past papers to do this. So the three steps of learning the key facts, testing yourself and practicing exam style questions are how you should be revising for A-Level Physics. Now in this revision session we're going to be looking at two types of questions. Firstly, general check questions designed to probe your understanding of the key concepts of the topic, and then assessment point questions, which are past paper examination questions which will mimic the types of questions found in public examinations. So let's start with these general check questions. The first question says, why does a wave diffract as it passes through a gap? So pause the video now, then unpause the video when you want to go through your answer. Well, a wave will diffract as it's compressed through a gap, which the wave that moves through the gap interferes and then produces a diffraction pattern. The next question says, why does little diffraction take place when the gap is much bigger than the wavelength of a wave? So pause the video now, then unpause the video when you want to go through your answer. Now, as the gap is large, the wave is not altered very much by passing through the gap, and therefore the interference process will not take place to produce the pattern needed. The next question says, why does little diffraction take place when the gap is much smaller than the wavelength of the wave? So pause the video now, then unpause the video when you want to go through your answer. Well, as the gap is very small, most of the wave will be absorbed by the wall, and then not enough of the wave will be present on the other side to form a strong diffraction pattern. The next question says, when is the most diffraction observed and why? So pause the video now, then unpause the video when you want to go through your answer. Well, most diffraction is observed when the wavelength is equivalent to the gap size it passes through. This is because when the slit width is comparable to the wavelength, all the diffracted waves will interfere constructively, resulting in a maximum of diffraction intensity. The next question says, when a wave encounters an object, why does a shadow form behind an object? Pause the video now, then unpause the video when you want to go through your answer. Well, a shadow forms as the object absorbs the wave, so there's no wave behind the object leading to the shadow. The next question says, when a wave encounters an object, why does a shadow not form behind the object over a large distance? So pause the video now, then unpause the video when you want to go through your answer. Well, as the wave diffracts, it hits the edge. The wave will diffract as it hits the edges of the object, causing the wave to spread out from this diffraction and fill in some of the shadow behind the object. The next question says, when a wave encounters an object, so why does the shadow form directly behind the object still? So pause the video now, then unpause the video when you want to go through your answer. Well, a shadow forms directly behind the object as the diffraction process has not yet occurred sufficiently at that point for the wave to be present behind the object. What property of a wave is altered during diffraction and why? Pause the video now, then unpause the video when you want to go through your answer. The only property of a wave that changes when it diffracts is its amplitude. That's because some of the energy is dissipated when a wave is diffracted through a gap. If in the same diffraction setup, blue light replaced red light, what would you observe in your diffraction pattern and why? So pause the video now, then unpause the video when you want to go through your answer. Well, the wavelength of red light is longer, so the light will diffract more, as the gap is now smaller than the wavelength, so the intensity fringes would therefore be wider. If, for the same light source, the slit was made narrower, what would you observe in your diffraction pattern and why? So pause the video now, then unpause the video when you want to go through your answer. If the slit was made narrower, the intensity would decrease as less of the wave is getting through, and the fringe spacing will be wider as more diffraction takes place. Why would this setup produce two coherent waves? So pause the video now, then unpause the video when you want to go through your answer. The wave will pass through the gaps, so it becomes two new wave sources. As both new waves originate from the same starting point, they'll have the same wavelength, they'll have the same frequency, so therefore they will be coherent. What will be produced on the far screen and why? So pause the video now, then unpause the video when you want to go through your answer. A pattern of maxima and minima would form as you get interference and superposition from the two waves produced from the gaps. When are bright fringes produced on the screen and why? Pause the video now, then unpause the video when you want to go through your answer. Bright fringes are produced when the path difference between the two sources is a multiple of a wavelength. This is because the waves will arrive in phase and constructively interfere. When are dark fringes produced on the screen and why? So pause the video now, then unpause the video when you want to go through your answer. Dark fringes are produced when the path difference between two sources is a multiple of half a wavelength. This is because the waves arrive out of phase and destructively interfere. What would happen to the fringe spacing if the distance from slit to screen is increased and why? So pause the video now, then unpause the video when you want to go through your answer. When the distance from slit to screen increases, the fringe spacing increases. This is because the greater the distance from slit to screen, the greater the wave can spread out due to diffraction, so the fringe spacing is larger. What would happen to the fringe spacing if the slit spacing increased and why? So pause the video now, then unpause the video when you want to go through your answer. When the distance from the slit spacing increases, the fringe spacing decreases, because when the slits are closer together, the path difference is smaller, so the light waves must travel less distance to interfere constructively or destructively. What would happen to the fringe spacing if the wavelength of the source increased and why? So pause the video now, then unpause the video when you want to go through your answer. When the wavelength of the source increases, the fringe spacing increases, because as the wavelengths are now larger, the path differences are now larger values, so the fringe spaces must increase accordingly. Why is it difficult to measure the distance between adjacent fringes in the Young's double slit experiment? So pause the video now, then unpause the video when you want to go through your answer. The distance from the centre of one fringe to the centre of the adjacent fringe will be a very small value, so this will give a large percentage uncertainty when this value is measured with a ruler. How can the accuracy of the fringe spacings be increased in the Young's double slit experiment? So pause the video now, then unpause the video when you want to go through your answer. Well, measure the distance between several fringes and divide by the number of measurements taken. This gives an average value and reduces random error. Now remember, when you're taking your values though, it's the number of spacings, not the number of fringes, that you will divide by. Why does diffraction take place when a wave passes through a diffraction grating? So pause the video now, then unpause the video when you want to go through your answer. A diffraction grating has many gaps in it, so the wave will diffract through each gap to produce a diffraction pattern. Why is the diffraction pattern from a diffraction grating bigger than the diffraction pattern from a Young's double slit? So pause the video now, then unpause the video when you want to go through your answer. Well, a diffraction grating has many gaps in it, whilst a Young's double slit has 2 gaps in it. This therefore means more light will pass through the diffraction grating. The next question says, why is the diffraction pattern from a diffraction grating sharper than the diffraction pattern from a young double slit? So, pause the video now, then unpause the video when you want to go through your answer. In a diffraction grating, the space between the slits is much smaller, so the fringe spacing is smaller and sharper as there's more instances of interference taking place. Which apparatus results in more accurate values being taken for fringe spacing, the young double slit or the diffraction grating, and why? So, pause the video now, then unpause the video when you want to go through your answer. Well, the diffraction grating, as the fringes are sharper, so it's easier to measure the gaps between them with a greater accuracy. What is the path difference between the waves at the central beam of an interference pattern? Pause the video now, then unpause the video when you want to go through your answer. The path difference is 0, as it's the 0th order of the interference pattern. What would happen to the angle to the normal if the distance between the slits increased in y? So pause the video now, then unpause the video when you want to go through your answer. If the distance between the slits increased, the diffraction effect is lessened, so the waves don't spread out as much before interfering, so therefore this will cause the angle to decrease. What would happen to the angle if the wavelength of the wave increased in y? So pause the video now, then unpause the video when you want to go through your answer. If the wavelength increased, the diffraction effect is increased as the wavelength is even greater than the slit space, so the waves do spread out more and this causes our angle to increase. Can an infinite number of orders of maximum be produced by a diffraction grating in y? So pause the video now, then unpause the video when you want to go through your answer. No, only a finite number of orders can be produced, as there's a maximum angle of diffraction, 90 degrees, as the diffraction grating is at right angles to the incident beam. If the diffraction grating experiment can produce beams up to the third order, how many beams will be on the screen? Pause the video now, then unpause the video when you want to go through your answer. There will be a maximum of 7 beams on the screen. There'll be 3 beams on each side of a central maxima and the central maxima itself. If a diffraction grating experiment can produce beams up to the 7th order, how many beams would be on the screen? So pause the video now, then unpause the video when you want to go through your answer. Well, there will be 15 beams on the screen. There will be 7 beams each side of the central maxima and the central maxima itself. What happens to the speed of the wave if it moves into a denser medium in y? So pause the video now, then unpause the video when you want to go through your answer. The speed of the wave slows down in a denser medium. An electromagnetic wave always travels at the speed of light, but in a material it travels at the speed of the light until it hits an atom. It's then absorbed and re-emitted, which takes a small amount of time. The more this happens, the slower the effective average speed. So the more dense the material, the more atoms that are in the way to do this. The next question says, what happens to the frequency of a wave if it moves into a denser medium in y? So pause the video now, then unpause the video when you want to go through your answer. The frequency of a wave is a fixed value. The frequency will be an unchanging value as it's due to the photons that make the electromagnetic wave, and thus it can't be varied. Why does a wave bend when it moves into a medium of a different refractive index? So pause the video now, then unpause the video when you want to go through your answer. The refraction effect is observed as the wave hits the new material at an angle, so not all of the wavefront will change speed at the same time. This difference in the change of speed for the wavefront will cause a variation in the speed across the wavefront, which produces the bending effect of refraction. Under what 2 circumstances would refraction not be observed in a wave when it moves between 2 media and y? So pause the video now, then unpause the video when you want to go through your answer. Refraction is not observed if the wave hits the new medium along the normal, as the wavefront will change speed at the same time, or if the 2 media had the same refractive index, as the wave would not change speed at any point. What is the change in direction in the path of a wave when it moves into a denser medium in y? So pause the video now, then unpause the video when you want to go through your answer. When it moves into a denser medium, the wave will bend towards the normal as the light travels between 2 points along the path that requires the least time as compared to the other nearby paths. Light travels more slowly in a denser medium and hence will therefore bend towards the normal. What path will be taken by the path of a light ray as it hits a triangular glass prism coming from air and Y? So pause the video now, then unpause the video when you want to go through your answer. It would appear that the light would be travelling parallel through the prism. The light ray would refract towards the normal when it enters the glass prism and then away from the normal as it leaves the prism, giving an impression of a parallel line. What would happen if white light moved between two different media and Y? So pause the video now, then unpause the video when you want to go through your answer. The white light would break up into different parts of the spectrum as the different colours of the light would each travel at different speeds in the new medium. Which colour of light would have a larger angle of refraction if white light was shone through the two media, blue or red, and why? So pause the video now, then unpause the video when you want to go through your answers. Blue light would have the larger angle of refraction as it has the shorter wavelength of wave, given the greater refraction. Which colour of light would spread out more if white light was shone between two media, blue or red, and why? So pause the video now, then unpause the video when you want to go through your answer. Blue light would spread out more in the new medium as it has a shorter wavelength of wave, giving a greater refraction. So why is the sky blue on Earth? Pause the video now, then unpause the video when you want to go through your answer. Well, white light enters the atmosphere after being emitted from the sun and travelling through space. Upon entering the atmosphere, blue light refracts more as it has a lower wavelength, so will spread out more, giving the sky its blue colour. Why is the sky red on Earth at sunset? So pause the video now, then unpause the video when you want to go through your answer. The light has had farther to travel to get to the ground at sunset. This means that the refraction and scattering of the blue light will have happened at a point further away from the surface of the Earth. This leaves only the red light to refract at this point, giving the sky a reddish colour. What is total internal reflection? Pause the video now, then unpause the video when you want to go through your answer. Total internal reflection is the complete reflection of light that occurs when a light ray travelling in a medium with a high refractive index encounters a boundary with a medium of a lower refractive index at an angle greater than the critical angle. Why does total internal reflection occur? Pause the video now, then unpause the video when you want to go through your answer. Total internal reflection occurs when the angle of incidence exceeds the critical angle. At this point, the refracted ray would have an angle of incidence in the second medium that is greater than 90 degrees, making it impossible for the light to continue into the second medium. Instead, the light is completely reflected into the first medium. When does total internal reflection occur and why? So pause the video now and unpause the video when you want to go through your answer. Total internal reflection occurs when a light ray moves between media of different refractive indices, because the effect of total internal reflection is caused by the refraction. For total internal reflection to occur, why must the refractive index of the second medium be less than the first one? So pause the video now, then unpause the video when you want to go through your answer. Total internal reflection occurs when a light ray moves into a lower refractive index. That's because as it moves to a less optically dense medium, the ray travels faster. This means it's travelling so fast that refraction is so extreme, it in fact becomes reflection. What is so special about the critical angle? Pause the video now, then unpause the video when you want to go through your answer. The critical angle is the exact point between two media where the light transitions from carrying out refraction into carrying out reflection. At this angle, the light ray will refract so much that it will start to reflect back into the medium. It's refracted so much it's bent back onto itself. How can the critical angle be identified? Pause the video now, then unpause the video when you want to go through your answer. The critical angle is when the reflected/refracted ray is moving parallel to the boundary between the two media. If the angle of incidence is below the critical angle, what will happen and why? So pause the video now, then unpause the video when you want to go through your answer. Below the critical angle, the light ray will refract into the new medium. This is because the refraction that's carried out at the boundary is small enough to allow refraction by transmission through the material. What types of wave carry out total internal reflection? So pause the video now, then unpause the video when you want to go through your answer. All types of waves will carry out total internal reflection as refraction is a property of all waves. What is the benefit of having a low critical angle when using total internal reflection to transmit data? So pause the video now, then unpause the video when you want to go through your answer. A low critical angle will mean that there are many angles at which total internal reflection will occur. This will allow a lot of data to be transmitted. What is the drawback of having a low critical angle when using total internal reflection to transmit data? So pause the video now, then unpause the video when you want to go through your answer. A low critical angle will mean that there are many angles at which total internal reflection will occur, so there are many varied paths for the data to take, so the data would spread out and arrive at the destination at different times. Fibre optics can be referred to as a single mode. What does this mean and why are they designed this way? So pause the video now, then unpause the video when you want to go through your answer. Single mode means that there's only one path that the light can travel in the fibre optic. This is achieved by having a very narrow core. This prevents the light ray spreading out over its journey or modal dispersion and would cause pulse broadening. Why can white light not be used in fibre optics for data transfer? So pause the video now, then unpause the video when you want to go through your answer. As the white light would travel down the fibre optic, the different colours of light would travel down at different angles, so the distance travelled would be different. This would cause the different colours of light to spread out, which is called material dispersion and causes pulse broadening. What colour light would travel in a fibre optic the fastest and why? So pause the video now, then unpause the video when you want to go through your answer. Red light will travel faster as this refracts the least when it hits a new medium. This means the path it takes will be straighter than the blue light, so it will travel in a faster time as they're both travelling at the same speed. Why must the fibre optic be made of a transparent medium? Pause the video now, then unpause the video when you want to go through your answer. Well, the fibre optic transmits information via total internal reflection. If the medium of the core was not transparent, then the information will be absorbed as it moves through the fibre optic. Why must the cladding of the fibre optic have a lower refractive index than the core? So pause the video now, then unpause the video when you want to go through your answer. Total internal reflection occurs when a light ray moves into a lower refractive index, the cladding. This is because as it's moving to a less optically dense medium, the ray travels faster. This means it's travelling so fast that the refraction is so extreme it becomes reflection. What is the benefit of having a fibre optic with a low critical angle? So, as mentioned before, a low critical angle means that there are many angles at which the total internal reflection will occur. This allows a lot of data to be transmitted. What is the advantage of using fibre optics to transfer data as opposed to copper wires? So, pause the video now, then unpause the video when you want to go through your answer. Well, the advantages of the fibre optics are that they're more secure, they have a higher bandwidth, a lower attenuation, they're much lighter, there's no crosstalk or interference, it's safer near high voltage equipment, it has longer transmissions without repeaters, and it uses more communication channels. What is the disadvantage of using fibre optics to transfer data as opposed to copper wires? Pause the video now, then unpause the video when you want to go through your answer. The disadvantage of the fibre optics are that the new infrastructure will be required, it's more difficult to mend or join together, and it can't carry electrical power that much. It will also break if bent too much. For a fibre optic, what is a digital signal? So pause the video now, then unpause the video when you want to go through your answer. In a fibre optic, the information is transferred via a light ray. So a digital signal is binary, so it consists of the light ray being on or being off. Why are digital signals used in fibre optics? Pause the video now, then unpause the video when you want to go through your answer. A digital signal is used is either 0 or 1 because even if the signal is distorted, the original signal can be restored at the end to be back to either 0 or 1. Now let's have a look at some exam style questions to do with waves. An engineering team designs a high-speed digital communication link between two islands using optical fibre laid beneath the sea. The fibre is constructed from a chlorine both made of silica-based glass with the following properties. A short pulse of infrared light is launched into the fibre. Initial measurements show the pulse duration to be 2 nanoseconds. After travelling a distance of 50 kilometers through the fibre, the pulse duration broadens to 5.5 nanoseconds due to dispersion and absorption effects. A researcher makes the claim that simply reducing the core diameter will eliminate pulse broadening entirely, ensuring a perfect signal integrity. Use the principle of Snell's law and total internal reflection, explain clearly why the optical fibre must have a cladding with a lower refractive index than the core. Calculate the critical angle at the boundary between the fibre core and the cladding and explain why this calculation is significant for signal transmission. From the data provided, calculate the percentage increase in pulse duration after travelling 50 kilometers through the fibre, and then critically evaluate the researcher's claim that reducing the core diameter will entirely eliminate pulse broadening. Your evaluation should discuss the roles of material dispersion, modal dispersion, and absorption. So pause the video now and unpause the video when you want to go through your answer. Okay, in this first one, the cladding refractive index must be lower to achieve total internal reflection at the boundary. Using Snell's law at the boundary, with end core being greater than end cladding, the refraction bends away from the normal. So this ensures that the angle of incidence within the fibre is greater than the critical angle, trapping the light within the core. Without this lower index cladding, the light would refract out, causing a signal loss. Now we know sine critical angle is equal to the end cladding over the end core. So you work it through to be 78.5 degrees. Now the critical angle is significant as it's the minimum angle for total internal reflection. So light must strike the boundaries at angles greater than 78.5 degrees to remain trapped, ensuring efficient transmission. Now the percentage decrease is going to be 5.5 minus 2 over 2 times by 100, which is 175%. Next, we know reducing the core diameter helps decrease modal dispersion by restricting the number of possible paths. However, material dispersion still remains due to the properties of the glass. Absorption is also unaffected by changing core diameter, so still broadens the pulse by weakening the intensity. Thus, even if the modal dispersion is reduced significantly, material dispersion and absorption still limit how sharp the pulse is. So the researcher's claim is incorrect. Reducing the diameter does help reduce pulse broadening, but can't eliminate it entirely. You need to combine the optimization of multiple factors to get the best performance. On a hot day, an observer notices distant objects such as trees appear to have reflections beneath them, despite the absence of water. This optical phenomenon is known as an inferior mirage. A physics student investigates this by measuring how the refractive index of air near the ground changes with temperature. They collect the following data at various heights above a hot asphalt road. The refractive index of the cooler upper air is approximately 1.000293. The student hypothesizes that the total internal reflection within the layers of air is responsible for the mirage. Explain clearly why variations in air temperatures above a hot surface changes the refractive index. Calculate the critical angle at the boundary between the air layers 0 cm and 100 cm above the ground. Explain clearly what this calculation implies physically about light rays travelling through these layers. And then finally, evaluate critically the student's hypothesis that the total internal reflection within the layers of air is the cause of the inferior mirage. Consider the strengths and limitations of this hypothesis in the context of your data analysis. So, pause the video now, then unpause the video when you want to go through your answer. Okay, hot air is less dense due to the expansion, and cooler air is therefore denser. The refractive index depends on the density. The less dense air has a lower refractive index, and the denser air has a higher refractive index. Therefore, the temperature gradients near the surfaces produce refractive index gradients as well. Now, we know that sine critical angle is n upper divided by n lower, so you work it through, and the critical angle will therefore be equal to 1.00029 before we take the sine of that. This is slightly greater than 1, so it physically implies that the layers are extremely close in the refractive indices, so the true critical angle calculation isn't achievable directly between these two layers, since the total internal reflection strictly requires a lower refractive index. So the gradual refractive index gradient rather than a sharp boundary is needed, so thus the continuous bending rather than one single reflection occurs in these mirages. Now, the refractive index gradient is clearly supported by the data and explains why the light is bending towards the regions of a high refractive index. The observed trend indicates conditions for refraction are plausible near the ground surfaces. Now, the total internal reflection strictly requires discrete boundary layers with a significant index difference and defined interface, which is not shown in the data. Now, real mirages typically involve a continuous gradient refraction rather than a discrete boundary reflection, which better describes the observed mirages. So the hypothesis has got merit, but oversimplifies the scenario. A more refined hypothesis involving a continuous gradient refraction rather than a strict total internal reflection will be a more accurate idea of the situation. The next question says, a diving company investigates how vision underwater is affected by refraction. When divers use standard air-filled masks, they can clearly see underwater before attempting to see without masks. Vision is then severely distorted. The company's technicians record the refractive indices of relevant materials. A diver without a mask tries to view an object underwater. The technicians suggest that divers' inability to focus is due to refraction occurring directly at the water-eye boundary. Explain using refractive indices and Snell's law why vision is significantly impaired underwater without a diving mask. Calculate the critical angle for the boundary between the diver's eye lens and fresh water. Clearly interpret the physical meaning of your result. A researcher proposes that the divers would see better if the masks were filled with water instead of air, as would remove a refractive boundary. Evaluate this claim critically using the relevant data provided. And then another technician suggests increasing the refractive index of the mask glass substantially to around 2.4 to further improve underwater vision. Critically discuss this practically and potential consequences of this suggestion. So pause the video now, then unpause the video when you want to go through your answer. Okay, in this first one, without a mask, refraction occurs directly at the water-eye boundary. The refractive indices of the eye lens and the water are very close, reducing refraction at this boundary significantly. Now, most refraction normally happens at the air lens boundary, so underwater this boundary is effectively removed, resulting in a minimal focus and power. Therefore, the eye cannot focus correctly underwater, so it causes significant blurring. We know that the sine critical angle is n water over n lens, so the angle is going to be 70.2 degrees. Beyond this angle, total internal reflection occurs within the eye lens. So rays entering the eye at very shallow angles may not enter effectively, contributing to further impaired vision. Filling the mask with water would indeed remove the air-to-glass and air-to-lens boundaries, reducing refractive discontinuities. However, this would replicate conditions similar to the no mask, given a minimal refractive focusing at the surface. So the eye lens alone is insufficient for underwater focusing due to similar refractive indices. The visions would remain blurred, so the researcher's claim is incorrect. Filling the mask with water does not improve vision and essentially removes the benefits provided by the air-to-glass and the air-to-eye interface. Finally, high-index glasses are costly, heavier and more fragile, making them less suitable practically. Higher refractive index could indeed increase refraction, enhancing the initial focus and power, and the high-index glass will cause significant optical distortions like chromatic aberration and dispersion, which would potentially outweigh any focus and benefits and worsen the overall clarity. A research team is designing a compact spectrometer to analyse light from distant stars. They perform preliminary experiments using two setups. Experiment 1, a monochromatic laser with a wavelength of 650 nanometers is passed through a single narrow slit of width 1.5 times 10 to the minus 4 meters. They record a diffraction pattern produced on the distant screen. A white light source is passed through the same slit in experiment 2 and diffraction effects are observed. Separately, the team tests the diffraction gradient with 500 lines per millimeter at normal incidence to study stellar spectra. They observed that for certain bright spectral lines, the diffraction maximum occurred the following separations. Describe qualitatively how the diffraction pattern observed in experiment 1 would differ from that observed in experiment 2. Explain how changing the slit width would affect the width of the central diffraction maximum in both experiments. Use the information provided for experiment 1 to determine the angular width between the first minima of the central diffraction maximum. Then analyse the diffraction grating data. Estimate the wavelength of the light corresponding to the bright spectral line observed. Explain your method clearly. Comment on how the use of diffraction gratings help in the study of stellar spectra. So pause the video now, then unpause the video when you want to go through your answer. In this first one, monochromatic light produces a central bright fringe with symmetrical side fringes of decreasing intensity. White light produces a central white fringe, but coloured fringes appear at the wider angles. The different wavelengths diffract by different amounts, so the red spreads more than blue. The white light pattern will appear broader and more complex due to this wavelength-dependent diffraction. Secondly, narrowing the slit widens the central diffraction maximum, widening the slit narrows the central maximum. In both monochromatic and white light cases, the effect is consistent. Slit width inversely affects the spread. So for white light, the broader slit would compress all colour fringes, narrower slits exaggerating the colour separation. We know d sine theta equals n lambda, so you can work this through and you get theta to be 0.248 degrees. Therefore the full angular width is that times by 2 because it's either side of the central maxima, so it's 0.496 degrees. Finally, d sine theta equals n lambda. We know d is 1 over 500 times 10 to the 3, so therefore it's 2 times 10 to the minus 6. So therefore we work out lambda, we put all the values in, to be equal to 584 nanometers. This is a wavelength in the visible range. It's a yellowy-orange visible light. So the diffraction gratings will allow precise wavelength measurements by separating the light into distinct maxima. Essential for stellar spectroscopy, it will identify elements and determine redshifts. In a lab experiment, a laser of wavelength 640 nanometers is directed at a double slit arrangement. The slit separation is measured at 0.35 millimeters and the screen is placed 2.5 meters away to observe the resultant interference pattern. Later, the same apparatus is used with a white light source after adjusting the experimental setup to ensure a coherence between the slits. Observations and key measurements are recorded. The team also discussed how early experiments like Young's helped challenge the particle model of light, influence the development of the modern theories of electromagnetic radiation, explain why using a laser improves the clarity of the interference fringes compared to using an ordinary light bulb. In your answer, refer to coherence and path difference. Calculate the fringe spacing observed with the laser in the initial setup. Explain qualitatively why the interference pattern changes when the white light is used instead of the monochromatic light. The lab technician suggests that using a laser carries no safety risks because the power output is low. Critically evaluate this claim. Then discuss how the Young's double slit experiment helped advance the understanding of the nature of electromagnetic radiation and why it posed a problem for the particle model of light at the time. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, lasers produce coherent light, so they've got a constant phase difference and the waves have the same frequency. Ordinary sources like bulbs are incoherent. They have a random phase relationship, so there's no interference pattern. So the path difference between the laser waves at the double slits leads to a stable and constructive and destructive interference. Therefore, the laser creates sharper, stable, bright and dark fringes. We know that W equals lambda D over S. Pop in all the values, you get 4.57 times 10 to the minus 3 meters. White light contains ranges of different wavelengths. Different wavelengths will interfere differently, with their fringe spacings dependent on the wavelength. The central fringe remains white because all the colours superpose, whilst the outer fringes show a colour separation. Red fringes further away than blue. Now, even low-power lasers can cause eye damage due to the concentrated energy and focusing by the lens on the retina. Now, safety risks include temporary or permanent vision damage if the laser beam is directly observed, so therefore appropriate precautions are essential despite the low power. Now, Young's experiment demonstrated light interference, implying wave behaviour. This challenged the Newton corpuscular or particle theory of light, which couldn't explain stable interference patterns. So this supported development of wave models and ultimately influenced the understanding of electromagnetic waves as oscillating electrical and magnetic fields. A laser of wavelength 580 nanometers is used in a Young's double slit experiment. The slits are separated by 0.30 millimeters and the screen is positioned 2.0 meters away. The experiment is repeated with a different laser of unknown wavelengths, resulting in a measured fringe spacing 20% smaller than that of the original setup. The experimenters also observed the effects of slightly misaligning the slits and briefly exposing the laser beam to open air without beam controls. Describe the conditions needed for a stable interference pattern to form the Young's double slit experiment and why coherence is important. Calculate the fringe spacing produced by the original 580 nanometer laser. Determine the wavelength of the second laser that produces the fringe spacing that is 20% smaller. Explain with a reference to the path difference why bright and dark fringes form on the screen. A student suggests that misaligning the slits slightly horizontally would have no significant effect on the interference pattern. Assess this suggestion. Then the experimenter briefly removes beam limiters and warning signs from the laser setup during testing. Discuss the risks associated with this action and explain why specific laser safety protocols must always be followed, even with low-powered lasers. So pause the video now, then unpause the video when you want to go through your answer. Right, the two sources must be coherent, have a constant phase difference, and frequency and wavelength must be the same. The light from the slits must have a similar amplitude for clear fringes. Coherence ensures that constructive and destructive interference is stable over time. Without the coherence, the phase difference is random, which would cause the pattern to blur and disappear. W equals lambda d over s, pop in all the numbers, we get 3.87 times 10 to the minus 3 meters. We work out our new fringe spacing, which is 80% of the old one, so it's 3.096 millimeters. Pop in the values, we get 464 nanometers. Next one, bright fringes occur where the path difference between the two waves is a whole number of wavelengths. It's constructive interference. Dark fringes occur when the path difference is an odd multiple of half wavelengths. It's destructive interference. The path difference alters the phase relationship between the waves, leading to regions of maximum and minimum on the screen. Now, the slightly horizontal misalignment can cause the wavefronts to arrive at slits with slightly different phases. This reduces the fringe contrasts, so therefore the student's suggestion is incorrect. The misalignment would affect the visibility and the sharpness of the fringes even if the slit separation remains constant. Now, without beam limiters and warning signs, there's a risk of direct or reflected exposure to the eyes, leading to permanent damage to the retina. Laser safety protocols are essential even with low-powered lasers to prevent accidental injury. Now, a laboratory is analysing light emitted by an unknown distant star to determine its elemental composition. A diffraction grating 600 lines per millimeter is used in the spectrometer setup. The observed spectral data are as follows. The team notes that the second order, n equals 2, the violet line is at the limit of the detection system. Explain qualitatively why a higher order maxima appear fainter even for the same spectral line. Use the data to determine the wavelength of the violet and red lines. Show your full reasoning. Based on the calculated wavelengths, identify the likely elements responsible for the two spectral lines using the following rough emission data for elements. Then evaluate how confident you can be in this elemental identification based on the diffraction grading method alone. In your answer, consider the strengths, limitations, and any assumptions that could undermine your conclusion. So, pause the video now. Then unpause the video when you want to go through your answer. Right, in this first one, high order diffraction spreads energy over wider angles, so the diffraction efficiency often drops sharply for the higher orders, so therefore higher orders appear fainter for even strong spectral lines. Next one, we say d sine theta equals n lambda. D is 1 over 600 times 10 to the 3. So for the violet line, we can work it through. Lambda, pop it in there, pop the values in. We get 612 nanometers. For the red line, we do the same. We get 853 nanometers. 853 nanometers is outside the visible red spectrum, so you will need to not use that order, but the second order instead. And also, multiple lines may overlap at different orders, making it harder to make a judgment. 612 nanometers is close to the red oxygen line, but it's not perfect, but it could be plausible. That's that one. 853 nanometers is too high, so it's either misidentified or it's infrared. It's not one of the three lines given, so only oxygen identification has weak support, so we need some better data to confirm. Finally, diffraction gratings offer a higher angular resolution, leading to more accurate wavelength measurements. We can separate closely spaced spectral lines, which is ideal for stellar analysis. The overlap between the different orders could cause line misidentification if not accounted for. We may get observational errors which affect the wavelength calculation heavily. Only a few strong lines will be observed, and you could miss the weaker lines necessary for accurate identification. We assume normal instance and perfect grating calibration. Real setups often aren't perfectly calibrated. There's a reasonable first identification but needs cross-checking with other independent measurements, so you have a bit of confidence, but it's not enough for a definite elemental assignment. Following the early experiments, the research team wants to study very fine structures and interference patterns. They set up a double slit experiment using a narrow single slit with width 0.080mm placed in front of the double slits to limit the wavefront width. The set of parameters are shown as following. They observe a broad diffraction envelope within the double slit fringes which are modulated. Some fringes become very faint or invisible near the edges of the diffraction pattern. Explain why introducing a single slit in front of the double slits causes the double slit fringes to be modulated by a broader diffraction envelope. Calculate the angular width of the broad diffraction pattern caused by the single slit. Estimate the number of bright fringes visible within the central maxima produced by the single slit, and suggest one experimental adjustment that would allow for more double slit fringes to be observed clearly within the diffraction envelope. Explain your reasoning. So, pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, a single slit acts as the diffraction source, producing a broad diffraction pattern. The light reaching the double slits is now diffraction limited, affecting the overall intensity distribution. The double slit interference fringes are modulated in intensity by the single slit diffraction envelope. It's bright in the centre and it fades towards the edges. We know d sine theta equals n lambda, so we can pop it all through. We get theta to equal 0.415. The angular width is between the two max minima on either side of the central maxima, so you double it, it's 0.83 degrees. Now we know change in theta equals lambda over s, so you can pop in the values and we get it to be 1.93 times 10 to minus 3 radians, which is 0.11 degrees. Now the number of bright fringes in the central maxima is 0.83, which is the overall angle we just calculated, divided by 0.11, so it's 7.5, so rounds down to 7. Now, what we could do is decrease the slit width. A single slit is wider and a narrow diffraction pattern, or you could increase the double slit separation. This would either of them would narrow the diffraction envelope or increase the number of fringes fitting in it, improving the visibility across the pattern. A ray of monochromatic light is incident on a glass prism as shown. Show that the refractive index of the glass for this ray of light is 1.89. State what is meant by the term the critical angle and calculate the critical angle for this light in the prism. Complete the diagram below to show the path of the ray as it passes through the prism and emerges into the air. So pause the video now, then unpause the video when you want to go through your answer. In this first one, we say n is equal to sine theta 1 over sine theta 2, pop in the values, n equals 1.89. The critical angle is the angle of incidence such that the angle of refraction becomes 90 degrees. We know that the sine critical angle is 1 over n, or 1 over 1.89, so theta equals 31.9. So what we can do is we can see in the diagram, we can draw in the values, we look at the laws of angles and we work out our values to get the following diagram as shown. Note we get total internal reflection for 1 mark. We can see that the angle it hits the second side at is 38 degrees. You'll get refraction away from the normal because we're now going into a less dense medium, and then it's going to be between 22 and 45 degrees. A student is carrying out an experiment to investigate the interference of sound waves. Two identical loudspeakers L1 and L2 are connected to a signal generator as shown. A sound level meter is moved from A to B and a series of maxima are detected. The sound waves emitted from the loudspeakers are coherent. State what is meant by coherent. Explain in terms of waves how a maxima is produced. Then the wavelength of the sound wave is 0.400 meters. The distance from L2 to the third order maximum at point P is 6 meters. Determine the distance from L1 to P. Then a second student in the room is wearing a pair of active noise cancelling headphones. The student switches on the ANC function. The sound level from the loudspeakers heard by the student decreases significantly. Name the type of interference that the headphones use to reduce the sound level. So pause the video now and then unpause the video when you want to go through your answer. Right, in this first one, the sound waves from the loudspeaker have a constant phase relationship, have the same frequency, same wavelength, same velocity. The maximum is produced when the waves meet in phase. We know the path difference because the meeting in phase is n lambda, so it's another third order, so it's 3 times by 0.4. That equals the path difference, so 3 times by 0.4 equals 6 minus the other path, so therefore the other path is 4.8. This must lead to destructive interference. Lighthouses are located along coastlines to aid navigation. A lighthouse emits an intense beam of light. In clear weather, the beam is visible for long distances, but in foggy weather, the visibility of the beam is limited. The beam is refracted by water droplets in the air. A light ray in the beam is incident on the spherical water droplet with an angle of incidence of 40 degrees. The ray passes through the droplet and meets the water-air boundary at x as shown. Deduce whether the ray leaves the water droplet at a point x. The speed of light in the water is 2.25 times 10 to the 8 meters per second. So pause the video now, then unpause the video when you want to go through your answer. Right, in this question we know that n for air to water is 3 times 10 to the 8 over 2.25 times 10 to the 8 is 1.33. So therefore we can say n sine theta 1 equals n sine theta 2. So we can say 1 times by sine 40 equals 1.33 times by sine theta 2. Theta 2 equals 29. So therefore we know that the critical angle, sine critical angle, is 1 over 1.33. So we know it's 49 degrees. That is greater than 29. So you get refraction. Calculate the largest angle theta to the axis at which the light can travel for long distances through the core of a multimode fibre if the refractive index of the core is 1.574 and the cladding is 1.550. Explain what would happen to the light entering the fibre at an angle to the axis greater than the angle calculated in 1.1. So pause the video now, then unpause the video when you want to go through your answer. Right, we know that 1.57 sine critical angle is equal to 1.500 times by 1. So therefore C is going to be 80 degrees. So therefore the angle, which is the opposite side to the critical angle, which must overall equal to 90, is therefore equal to 10 degrees. So therefore, if it was at a greater angle, then refraction would take place and the total internal reflection wouldn't happen. Now this means that some reflection or intensity would rapidly fall and the light would escape from the glass and the light will go into the cladding, so it won't transfer the energy efficiently. So that brings an end to our revision session today. If we've been successful and we've learned in today's revision session, we should be able to answer A-level physics examination style questions, assess our understanding on A-level physics, understand what topics we need to improve upon for A-level physics. So thank you so much for watching this revision session on waves, which is part of the paper 1 for AQA A-level physics, in particular looking at refraction, diffraction and interference. Thank you so much and have a lovely day.